Well, you're today. So that anyway. Oh, yeah. So that homework 7. It's one person had a lot of problem with A, and if you go, like, you can just put these into Chat GPT. Oops. Oh, I guess I didn't load that up there, but I just put the question on the paper into Chat GPT. I'll fix that link. Somehow I didn't put that up there, but anyway, it'll just answer the question. Like, it just, like, if you put the title of the paper and the authors, then just put the entire question in there, and the question has the other paper, it somehow can access those papers and put together an answer. It was pretty good. It was like I wouldn't take points off for it versus someone lost the entire question. So anyway, that's an option in desperation. Just do that, and then at least you could reword it, or something like that. But so anyway, that's that thing. Then we got, I want to go through this homework for today. There's that business and this business, and then this thing. This doesn't blink, right? Oh, it does. Open the new tab. That's good. All right. So, oh, and then also we have, let's see, I gotta go back to here, and we're doing surfaces. Need those slides too. So this paper is really about the blah 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 blah, and then it goes into this business about let's see, like this business, like contact angle, and then it goes into this thing. This is called the Newman. Should put that in here. It's called the Newman method or something, where you have this 3 phases meeting. You can figure out the surface tensions from the angles that you measure on the micrograph. So anyway, so that's the Newman method. It's in the notes. It's in the book. He shows kind of an example where you can get a micrograph. So this paper is not that. Let's see. I want it. This paper there. It's 2009, so it's old for our taste, but that's all right because it covers exactly what's in those notes. It does it like step by step. It's not in metals or ceramics, it's in polymers. So you have like for the plastics waste stream, you have like 80% high density polyethylene and polypropylene. So those are called polyolefins. So like carbon chains, carbon and hydrogen chains. So there's like the simplest polymers. That's basically 80%. Like this is polyethylene. And this thing up here is polypropylene. It's like everything's made out of polyethylene, polypropylene. So when you get the garbage, so again, this is going to go to the recycle place and they grind it up into shreds, and that, like Rumpke Recycling in Vine Street. And then they have a pile of shreds that are like mostly polyethylene and then like 25% polypropylene. Because everything is pretty much like that thing's the same thing, right? Everything is like that. So the problem is like polyethylene doesn't mix with polypropylene. In fact, no polymers mix at all. There aren't any polymers really. There's a couple, but basically there's none that mix. So you end up with situations like, then you're going to put that into a mixer at like 200 or 120 C or something, like 180 F. They end up with something like Swiss cheese, like this stuff, which isn't, it's going to have failure along the interfaces. So so it's difficult to predict exactly what you're going to get out of that. It looks like a mess. So, but all this is governed by the interfacial tension. So the surface tension of all these phases with respect to each other, like polystyrene, high density polyethylene, interfacial tension, polystyrene, polypropylene, interfacial tension, polypropylene, high density PE, interfacial tension. So depending on what those numbers are, interfacial tension, you can get all different kinds of setups going on with this. And in fact, you can get something like where you have little beads of one phase, like decorate the other phase. So here, polypropylene and high density polyethylene don't like each other. But the polystyrene has some kind of affinity for high density. So the polystyrene you put in, which is there's probably an example of that here somewhere, like a Scotch tape container. The plastic ones that are clear is polystyrene. Right? So that's immiscible with everything, you know. So anyway, that's locating on the line. The one they don't do is PET. I don't know why, like a water bottle. You know, that's the one that's most recycled, in fact. But I'm not sure why they don't mix that in with their mixtures of things. But they have PMMA, which is plexiglass. So they have in the nylon, polycaprolactone. Then they have biodegradable plastics. They have polylactic acid. Then they have poly-L-lactic acid. The polylactic acid has this has a polyester like this, and then it's got a carbon here. It's hydrogen. So 1, 2, 3, 4. So that guy's he's got 4. And then, you know, this is polyester, right? But this thing's planar. That structure is planar, which means that, or actually, this whole thing is planar. So basically, this carbon can be here. That's PLA, or that carbon can be here. That's PLLA, poly-L-lactic acid. They have different melting points, different everything. Like, so they're different. They don't mix with each other, even though it's just a switch of a thing from some. And polyethylene, like this, these are hydrogens, and polypropylene is like that. So it's also almost the same thing. 1, 2, 3, 1, 2, 3, 4. That polypropylene. This is also a thing that can have tacticity, like you can have the carbon kind of in the A position or the B position. So it can be isotactic, are always in the A position. And isotactic and symbiotic and heterotactic polypropylene are mixed. None of them mix. And you can have polyethylene that's like linear high density polyethylene. And polyethylene that's got long chain branches in it. And you can have polyethylene that's got kind of this arboreal thing, low density polyethylene. You can have polyethylene that's got like regular branching like that. Linear low density polyethylene. None of those mix. They're the same thing, they don't mix. None of those things mix. So basically, you're always going to have this situation where if you try to throw it together, you're going to end up with something like this. So you try to put and one thing you can do to make like plastic wood, you throw a compatibilizer in, and people have like worked on kinds of compatibilizers. So they put in like something that here they call SEB, which is styrene ethylene. So it's polystyrene and like that. It's got an aromatic ring, hydrogens, and then ethylene like this. And then butylene is 2 carbons inside, so it's butyl. It starts with this 1, 2, 3. It's got 1, 2, 3, 4 carbons. And then unsaturated here, so it ends up with this ethyl branch on it. So propylene has one carbon as a branch. Butylene has like 2. None of these things mix, you know. So basically, this thing can compatibilize somehow all these, and like they don't know why exactly, except, all right, so this paper kind of answers why, like why it compatibilizes, but so high density polypropylene and then like a Scotch tape container is thrown in a small amount. So it's polystyrene little beads. And the polystyrene somehow goes to the surface of the high density polyethylene. And then if you put in some of this, it's called styrene ethylene butylene, and they also have styrene ethylene butylene. I think it's SBE or something, but these are copolymers like these things, those things. I think they're random copolymers. You just throw it all in and polymerize it together. That stuff somehow does this. It takes these little polystyrene beads and then makes them go to when you put 1% of that copolymer in, polystyrene all of a sudden just goes to the surface of the phases of the high density, right? So then you have, so basically at that point, this thing looks a lot like what they call Pickering emulsion. Okay, so the Pickering emulsion is when you take oil and water, mix them together, and you put some uh, like powdered sugar in. The powdered sugar goes onto the surface of the oil droplets and makes an emulsion so that the oil's like suspended in the water by the sugar, which is hydrophilic, but the sugar doesn't dissolve. It just makes like a coating of a powder. So that's what like a Pickering emulsion. So you have like an insoluble powder kind of on the surface of the oil phase in the water. And then there's also a thing called let's see, there's another thing that he brings up in here. Let's see, he says Pickering Bejel or a Bigel, which is a Bigel is, it's a kind of Pickering emulsion. It's a bicontinuous interfacially jammed emulsion. So it's a Pickering emulsion where the thing's spinorally decomposed and the particles go to this interface of the spinol that forms. So that actually would be a good thing to give for a paper, but I didn't do that. But anyway, it's kind of interesting. You have a combination of spinol decomposition and the surface energy thing coupling together. And so in the other thing, like this isn't necessarily unique, like this business of the surface decoration, like a Pickering emulsion, is something that happens a lot. Like you put filler like carbon black into butadiene rubber with SBR phase, they're immiscible. So you have the three things mixed together, and the carbon black is supposed to reinforce the rubber, but it'll, in some cases, just do this Pickering emulsion thing and decorate the SBR phase. It's like whatever that is. So you can get this showing up a lot. Like this is pretty common. So one issue is like, well, why does that happen? Like, well, how would you predict that if you wanted that to happen? Like you want to be able to control it. And the whole thing is governed by the surface energies of all these phases that are here. So basically, that's what they're going to do in this paper, is to figure out if you have this micrograph, and then you can start measuring like angles on this, similar to what was in the notes. So you can start doing this kind of angle measurement, and from the angle measurements, you can figure out the surface energies. So these are all binary mixtures, alpha, beta, right? These are all ternary mixtures or quaternary mixtures. So 3 or 4 things mixed. So then if you have 3 things, there's only a limited number of things that can happen. Like they're all shown here. If you have 2 things, these things happen. If you have 3 things, it becomes a lot more complicated. You get to this, he shows a picture of what can happen from 3 things there. So 3 things like A, B, C. So C can like A, so C coats A, and C can like B less, so it's in between A. So C likes B better than A likes B, but C likes A. This is like how people would be, right? So you can have, anyway, people could be like this too, or anything's like this. So C likes A and B. C likes A more than B likes A, and then so C is going to go at the surface of A, and then you can predict all these other ones too the same way, right? So that likes means that there's an affinity coefficient, which is based on the surface tension. So he has this expression for the surface tension. So if you have BAC, it's so you're going to get a setup where you have BAC, like B. Let's see, BAC should be like B and C. Oh, all right. So here, like, right. Yeah. So these things refer to like ACB would be like if you have a series of A with C separating to B. So this term would be the important term of this setup, right? You have ACB. So anyway, he comes up with an equation like these interfacial tension ratio. He ends up with these expressions that can predict the behavior of the thing. That's the bottom line. So that he can come up and predict, like, all right, first off, from these micrographs, like phases like this, he can calculate the surface tensions of all the components just from the geometric features of this. So he's got kind of a problem, like when they meet, so you can't, what you want to get is the contact angle at the contact point. So he calls this a line. It's a point in 2D, but it's a line in 3D. So it's a line coming out of the paper, right? And then, so he calls that a line. That's a point of a line of contact, line of three-phase contact. And at that point, you would want to know what's the contact angle of one of the fluids, like phase A with the other fluids. But you can't exactly measure that. So he comes up with a construct where he can get the curvature of phase A at that point. So in other words, he shows down, this picture doesn't exactly show it, but basically in the micrographs, he shows how to get the curvature. So he's gonna draw a circle at that point of three-phase contact, right? So this kind of hairy thing at the top that you can barely see, you can blow this up, is the high density. Oops, there. This is like low resolution too. Did I do something weird? I don't know. This is actually getting pretty weird. Let me see what I do. Did something bad. Oops. That happened. I lost the entire system. That was a mistake. Well, that could work. Is there something like reduce? That doesn't work. Oh, escape kind of worked, right? Does this reduce? That only reduces there. I reduced for the whole thing. No, I did the whole guy here.
Hold down control and it's hold.
Ah, that helped. Well, that helped this. I use the control minus plus thing that I do all the time. That didn't, oh wait, this thing might do it. Maybe this does it. But yeah, that helped. All right, now I need to use the width. Okay, thanks, that helps. Except it's a wrong window, that's a the surface. That paper. Anyway, that did help a lot. Yeah, that works good. All right, so anyway, so that's how he gets these angles. He shows here kind of how he gets it's still confusing. Basically, he's saying that's the three-phase contact point. He's going to draw circles for the different phases. Then there's going to be a radius for the circle. I don't fully understand this. And then he draws a line. I'm not sure why he orients a line like that. There's probably a reason. But whereas radius for the artificial circle that he drew at the point of the line intersects that, then he can get this angle phi. And from phi, you can get the contact angle theta using equation, one of the equations here. Here, so from that phi, you can get the contact angle for A. And then same for B and C by drawing circles at the contact line, three-phase contact line. So it's geometry. I think this is just geometry, but I didn't really have time to figure out exactly how he did that geometrically, but basically you can figure it out, I think. So there's two ways. So if you have this kind of situation and you want to know that, first of all these things for this lambda is the spreading coefficient for the three phases he's going to use. And he gets that, he needs to know the binary, so it's a ternary spreading coefficient. He needs the binary surface tensions. So how do you get those in this kind of garbage mixture that he extruded, right? So you get those, there's two ways to get those. One way is this breaking thread method, which is published in let's see, 1990, right, by these guys in the Netherlands, right? So basically, if you take a thread, and this was developed not for plastics, but I think this is applying it to plastics. So originally developed for anything. But basically, what he does in this paper, in our paper, is he makes a thread of the different plastics. Then he makes a sandwich of it. So he wants to get it like polystyrene, high density polyethylene surface tension. So he makes a thread of polystyrene, and he makes two sheets of polyethylene, and he squishes them together. And then he sticks that into an optical micrograph, and the thread decays into, like the thread wants to decay into blobs, like kind of just a normal surface area reduction. So it's got a high surface area with the fiber and it wants to become spheres. So the process of it turning into spheres involves this oscillating feature that shows up. And then the amplitude of that oscillation, so it starts with A0, and then this is A. So A is going to be larger than A0, and it'll gradually grow into a sphere, like just over time. So the time dependence of that growth, that growth is driven by the surface tension, and it's also mitigated by the viscosity of the fluid that's in here. So basically, there's going to be an equation that has, so A is a function, so A is a function of A0. So A by A0, the ratio is an exponential of this Q times T. Let's see if I can open that up there. And Q is the surface tension. And then an omega number that this paper calculates. So it's a tabulated function. Then the viscosity, it depends on the initial radius of the fiber that you put in it. So it's pretty kind of a simple way to get the surface tension for a binary. Make sure it doesn't work for ternary, but you can get it for binary. Right. So the trick is that all the things he does here, he needs to know the binaries in order to get the ternary. Right. So that's one way. So he gets it that way. He can also get the binary surface tensions between the three phases, the AB, BC, and AC. He can get those also by this construction. This thing about figure out at the three-phase contact point, then what is the circle that would be the curvature at that point, draw a radius, then have this line, which I don't know how he orients this line. It looks like the line goes through the middle of two of the phases or something. Anyway, so I guess you have a matrix phase and then two phases that are separated. I'm not sure how you do it with the other ones, but he shows it in the paper how to do it. But you take from that contact point the radius of the curvature to that point where it crosses here, gives you this phi number, and from the phi you plug that into this geometric equation that gives you the surface tension, gives you contact angle, and we use the contact angle, the cosine equation to get the surface tension. Right? The thing from class, I think the homework asks you to get that, but the contact angle's up above this, like right there. The Young-Dupree law. So you can get the two-phase energy from the contact angle. And you get the contact angle. You get the contact angle from his oops. His thing here. Yeah, once you have phi, it's like equation 4 or something. Say not 4, not 2. It's not 1. I guess it's down below here. So once you have the phi's from that construction, then you can get the contact angle, and then cosine of that gives you the cosine of that angle gives you the surface tension. So you can basically get the surface tension from that. So that's kind of what's going on here. Let's see what else. So he says, like, he doesn't mention that this is for recycling. I guess 2009, they didn't realize it was for recycling. Like, I'm not sure what they were. He doesn't mention recycling this. I think it's kind of odd. This is directly what you would have to do if you were going to make plastic lumber from garbage. So that's pretty much the recycling business part of it. So from these, so he has conditions like he calculates the spreading coefficient. He didn't invent all this stuff. So you see it's referenced, right? So all this stuff is just kind of put together here. So in the diagram is basically from metallurgy, the idea of the surface tensions and how you can calculate from the shape of it the surface energy, right? So the stuff's kind of borrowed and put together, but it's pretty nice. Actually, it's a pretty nice paper because it tells you exactly how to do it. In fact, gives you at least 2 methods to do it. So like the the fiber, what's it called? The fiber breaking. What's it called? It's in the title, right? Visual tension inquiry, partial, no. It's like the fiber breaking method, I think, which is the one from that other paper. And then this method is he calls it the Newman projection method, or not Newman, just the Newman method is the thing from what we have from the notes. So in order to do this, he has to make sure that the system's quiescent. In other words, it's reached kind of a local equilibrium state. I mean, equilibrium would be like A, B, C stacked up, right? And you wouldn't have any droplets. So this is a metastable equilibrium. But he has to be sure that the phases are spherical. I mean, they have to, in other words, they can't be, in other words, he puts it through a mixer, so the phases are actually going to be stretched out. And then he anneals it for a while to get them so that they're spherical, so you can get that contact angle from that curvature thing. Right. So that's kind of what he's doing here. And then because it's ternary, it's not just this binary surface tensions, you have to calculate these other numbers, which are called spreading coefficients. And they're calculated from the binary coefficients. And then once you have the spreading coefficients, there's four options where you have spherical domains. So you have one of them can be negative. So if it's like that, and that one's negative, then you have BAC, so you have B, it's set up like this. You know, if you have one of them negative, it's at BAC1, then basically you're going to have this set up. It's going to be a domain coded by C with B. If you have the ACB1 or the BAC1 is negative. Let's see. This one's two negative, or one, which one's negative? Is the ABC one. So you have ABC set up. And the other two are positive. And this one's, the BAC one's negative. So it depends on the phase composition too, what you get, right? So basically all these would be like one of them's negative. So it doesn't matter which one, but basically this one's where you have a majority B phase, and then second A phase and minority C phase, right? So in that case, depending on how this works, if it's BAC that's negative, then you get A and C droplets inside B. In other words, B wants to be with A and C and A don't like each other. And then you have a case where you have two negatives, I guess, in this case. Let's see, one positive. All three have one positive. BAC end up with the reverse of this thing. We have C in the middle, A and then B. And then if you have two that are, or if all of them are negative, then you get this setup. So then you have a line of three-phase contact. So the place where he would apply this business is when you have a line of three-phase contact, and that's basically when you have three negative mixing coefficients, none of them want to mix, then you get this setup. So it's mostly geometric arguments and things in here. It's not a hard paper to read. No, it's pretty straightforward. I mean, if you don't know polymers, it might be a little shocking to see the polymer names, but basically you can just think about them like liquids, just liquids that have surface tensions with each other. So this is the copolymer, that's miscibilizing agent. He gives them molecular weights, melt index, viscosity. So because he's going to use the viscosity in that equation, just when he does the fiber breaking method, he needs viscosity. So he spends a little bit of time talking about the viscosity measurement. And this is a plateau viscosity. So polymers have shear thinning behavior. So polymer, you plot log of the viscosity versus the shear rate. So basically usually you have like a plate and plate, and you're spinning this at some frequency. That frequency gives you the rate of strain, like D strain, D time. So that's this thing. And then there's a torque involved in that. So the torque making it spin, so it's kind of a force, and then kind of force per area gives you the shear stress, right? And then basically the shear stress is related to strain rate by the viscosity. And that's the standard way for flow. Right? So this gives you the viscosity. And with indices is 1, 2, 1, 2. So this thing would kind of be viscosity 1, 2, 1, 2. If you wanted to do the thing with the C, you had to go on. Basically, this is just called a viscosity usually, because usually just don't shear. Anyway, as you increase the strain rate, say polymers that are like that, and then as you increase the strain rate, they kind of line up. So think about like uncooked spaghetti and cooked spaghetti. So uncooked spaghetti just falls out of the box. Cooked spaghetti is like a lump, right? So that means the viscosity of uncooked is high and the viscosity for that is low. That's called shear thinning and ends up being a power law dependence. If viscosity goes with the shear rate to some power. -2 is 1 power. And then there's a trail over. And this thing, like 1 over that shear rate is this relaxation time for the spaghetti, whatever the straight spaghetti can relax into the other ones. There's a time constant associated with the spaghetti transitioning from being straightened out to going back. At this rate, the time related to that is slow enough that the things can relax. Then down here, you get a Newtonian viscosity. Newtonian means it's constant. This number is a constant in that equation. Doesn't depend on the shear rate. Anyway, that's also called the plateau viscosity. So he's kind of looking for that number, and that number is this eta 0 number. So he measures that with the viscometer. Basically, this kind of a cone plate viscometer. You put the glue in there and you spin it. And you measure the torque. Usually oscillatory, but basically it could be straight. And then he plots that number here. So this is the plateau viscosity right here, Newtonian viscosity. Right. So another way so this is the complex viscosity, which means it's got a storage and a loss part to it. And they take the absolute value. So you kind of compare these two numbers. This is done at 25 inverse seconds. That's like somewhere here, right? But that's like a frequency or a shear rate number. So it's going to be strains unitless per time. So that's somewhere here. So it's a lower number than the plateau. And that's what he sees, like 0.42 versus 1.1. So it's shear thinning. Some things can shear thicken like egg. Like when you stir up egg, it thickens as you stir it. And then there's a couple other viscoelastic kind of behaviors, but shear thickening usually means that the structure changed. Like you change the structure of it. It's kind of a permanent one-way street thing. Shear thinning is this reversible, also structure changing. Anyway, he measures all that. Melt index is you take it's a measure of the flow. So you take a cup of the stuff, you heat it up to like 120, so it melts. And then you put a weight on top of it. And then you just measure how much weight comes out. If it's going to ooze out, you weigh that over a certain length of time. So the higher the viscosity, the lower the melt index. The lower the viscosity, the higher the melt index. So that's why he's got melt index. And then the one with the high viscosity has a low number, 5.5. And the one with the low viscosity has a high melt index, which means more goo came out because it's less viscous. That's it. So these are all. This is kind of an industrial paper. Like this melt index is like an industrial measure of how you just describe a polymer in an industrial setting. And then these other numbers are more analytic, I guess. In other words, if you buy plastic from Lyondell, they're not going to give you the molecular weight. They're going to give you the melt index. And that can give you the viscosity. It'll just give you the melt index, describes like the different grades of plastic. So that's why he's given that here. So let's see, what else is in here? He does that breaking test. Then he's got his polymers. These are the compositions he makes. And then he does that thing. So he makes a fiber of one of the polymers, puts it in a sandwich of the other polymer, and heats it up. And then he does micrographs and he measures the oscillating, the sine wave of the fiber as it grows with time. And this is the log of that. Sine wave is a function of time because it's supposed to be an exponential function. Right? The wherever it is. Gamma, blah, 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 it's in the other paper. Oops. Here, so this thing, alpha equals alpha 0. So you have to take log of the alpha by alpha 0 to get Q times T. You want to get Q, so you have to take a log. Has to be a log plot that he does. So it's log of the alpha by alpha 0 versus time, and the slope of that's Q. And so this is a high Q, that's got a low Q. It means this has a high surface tension and that has a low surface tension. Right, so it's kind of a nifty thing to do. Whoever thought it up, it's kind of bright, to figure that out. It's a simple way to measure it. So he gives he compares the methods in here in the table. Someplace it's got a table where he compares the breaking fiber method with the here. Materials characteristic. Somebody's got the breaking fiber method versus the Newman method for the surface tensions. Breaking thread. They don't even call it fiber, they just call it thread. So let's see, there's definitely a table in here of that stuff. Gamma. Number of measurements, interfacial tension by the breaking thread. So there's this breaking thread interfacial tensions. And then he compares the two here somewhere. Yeah, UBC. There's a table of comparison. The numbers come up kind of the same, like not exactly the same, but pretty close. And he gives some kind of argument for why they differ. I mean, he gives an argument about depending on what this angle is from this. If that angle gets small, the error gets larger. Put it that way, and you can kind of see in the equations he has that would be true. So the larger the contact angle that he has, the better resolution he has for the surface tension using his Newman method approach to the thing. So, that's about it, I think. Let's see. Let's get all these things. I mean, it's exactly what's in the book, what's in the notes. So it's pretty good that there's a paper that's exactly the same. It's in polymers. The book is about metals, but it's the same thing. It's more elaborate because he gets into this Pickering emulsion business and he explains why it happens in the paper. Like why is it transition when he adds that copolymer, it goes from that to that. So there's quite a bit of difference. In other words, here you have the polystyrenes all beads all over the place, and you put in 1% of that copolymer, and all of a sudden it all sticks to the surface. And using this method, he can calculate the number of these copolymers per nanometer squared on the surface of the high density polyethylene phase, which is kind of interesting. So just from a micrograph, you can tell how many molecules are on the surface of that droplet per nanometer squared. I mean, it's kind of impressive. I mean, he's using, like he's on a micron scale. He's measuring, he's telling you about nanometer scale things just by using his brain. So it's kind of useful. He mentions also that, so both the polypropylene and the high density polyethylene crystallize. So when they're mixed, they're in a melt. So they're liquid. And then as you cool it down below 100 C, they both crystallize. So high density makes these fibrillous crystals. And the polypropylene makes smaller crystals that you can't see at 5 micron. But the polypropylene is 80% crystalline, and this is probably 70%. So they're both pretty highly crystalline. And he says something about that because of that, there's a contraction, like the phases get smaller. So there's some kind of separation, but he said it doesn't matter. Like he has some cases where it doesn't separate and some it does. He gives the same answer. He mentions that in here. So it's a lot. I think it's a pretty good paper, I think it's kind of interesting to me. I mean, he's taking just pictures and he's getting thermodynamic information just from the pictures, which is the same as what's in the notes. This link is in the homework. It gives this Newman, this is the Newman construction here. So this gives, kind of describes it in this wiki page of ideal surface. This is the breaking fiber method. And this thing is just a paper I found. It talks about Pickering emulsions and kind of a more, because Pickering emulsions have been around since the 1800s, right? So it's not a new thing, but this is Janus particles. So Janus particle means like half of it. Janus was the Greek god that had two faces, like a face in the front and a face in the back. So basically, if you make nanoparticles that have different faces, and mostly what this is used for is self-propulsion. So you have one face that reacts with hydrogen peroxide and makes oxygen, and that's pushed out, and the particles can fly around. So you can, if you put just one side that does that, you can propel the particles, and you can turn that on and off by the hydrogen peroxide concentration. So they're doing that with a Pickering emulsion there. They're kind of showing a picture. You have water coming in and gas coming off, and that drives the particle. It's a platinum only on one side of the particle. So to make this, you get particles that separate between two phases. So they locate at the interface, and you dope one side of the thing so that the side that's facing up gets coated with the platinum, and then they'll just fly around. So people, there's like there's a huge number of PhDs on this kind of Janus particle motion and trying to control it to make micro machines, nano machines, or whatever. You know, so people, it's not that hard to do. Like anybody can do this, but basically, and it's unlikely to actually lead to anything useful, but basically people like things that fly around, and you can control how it flies by how you code it that way. So like this, see, this is a typical for this kind of hydrogen peroxide propelled nanoparticle. We could get a diffusion pathway, but it's got a preferred direction. So you can say, like, I'm making them go over here. I mean, so you'd have like a concentration gradient of like hydrogen peroxide across your fluid, and you can make them go away from the hydrogen peroxide. Or you can, I mean, it's conceivable you could do something with that. I mean, move nanoparticles where you want them to go. No one's done that. I mean, no one's made like a device for that, but basically it's an idea that's popular. And I mentioned that thing. So that's kind of everything for that. Let's see. So anyway, so what are the questions here? What the spreading coefficient is. So you have binary mixtures. So you have like, the contact angle would be like air, water, and the surface air and surface water. So you have two things that are mixed. So you have a three binary surface energies, right? And then if you have ternary, you need something else because you're gonna have to have this three component term. So that's the spreading coefficient to describe ternary mixtures. And then how it could be used, that's what this whole paper is about, is how it could be used for ternary mixtures to describe what the structure is going to be. So you can either use the structure to calculate, or you can calculate the structure from the numbers. It could go forward and backward. So that means you can predict, in other words, what should you mix into it to make it have the structure that you want. So logic behind equation one. Logic behind equation one. Equation one. So equation one is how you calculate these things. So you have three, so they're going to be, the dominant term is like AC. So in the case of one, if ABC, so ABC has this AC lead term. So if that's negative, then you're gonna, let's see. That means A and C have a high, have a, if it's negative, A and C have a low interfacial energy compared to A, B, and B, C. That means that A wants to be near C. If this is negative, A wants to be near, A and C want to be together. Right? So whichever one, A, C, and then B is left out, the guy in the middle. So if you have a negative gamma A, B, C, that means A, C are going to stick together. If it's positive, it means B, C want to be together. So it's positive here, so they have B, C together. This one's positive, that means A, B, A, C want to be together. So the logic is like, if that thing's bigger than the other two, if that thing's smaller than the other two, then it'll want to, those things, A, C will stick together. I mean, so it's basically the logic is just like which one's larger than the largest one. The smallest one will make them stick together. Like if this is negative, the thing's smaller than those, and then that means A and C stick together. If that's positive, that's larger than the others, that means you get this set up basically. So that's the logic behind it. So you have to kind of work that out for yourself, like what the logic is for that. Something kind of like what I said exactly. So use figure 1, you can kind of argue why those equations would be that way. Figure 2 shows the 3 contact angles. The description of contact angles in the notes, which is like this thing. And in the book to explain how the contact angle and surface tensions are related. Figure 2. So that's just the cosine of the contact angle with the surface tension. That's basically what related in figure 2. Figure 1, figure 2. So that's kind of used here. So you have like the contact angles are here and the surface tensions. So basically the surface tensions are like a force balance. He explains it in this paper, like you can read it, but basically there's a force balance along that line of 3-phase contact. And then the contact angles are related to the surface tension here. It's also described in that kind of force balance for this is in like, kind of like here, I guess. So this is a force balance for the contact angle. So you could use that. It's like slide 26 describes how the contact angle through a force balance, so you do a projection of this contact angle onto so you're doing a force balance along the surface. So it's like this surface energy versus that surface energy are pulling against each other. So it's this minus that. And then it's plus like this times cosine of the angle to project that one down onto the surface. Then you just do a force balance along the surface. And because the cosine of that, you end up with cosine of the angle gives you the surface tensions. That's basically the Young equation for contact angle. So that's what the kind of height is of that one. And then that's just applied. So in figure 2, and that same idea is just applied to a ternary system, which is also done in the notes. For a ternary system, it's done like here. Right. So it's in the book, it's in the notes, and it's on the wiki page too for whatever that is. I think this thing probably, yeah, this has a ternary system in it. So it's described in the notes here in the book and in the paper. So there's like 3 places where it describes whatever that says. What's going on in figure 2, basically based on the contact angle thing. And then explain the Newman triangle and Newman equation. That's also in the notes. And there's a wiki page for this ideal surface thing. There it is. There. This is the Newman thing. So basically that's here. It's also in the notes, like what the Newman thing is. So I went through that in class. Yeah.
Should be.
Mm-hmm.
We will take reference from this.
Or,
It says use the description of continental in the notes and book.
mm-hmm.
So is it the note the description you were showing right now.
Yeah.
That three angle together.
Yeah. Yeah. But the paper is almost exactly what's in the notes and what's in the book. Like they're kind of the same. And there's a wiki page. That wiki page for ideal surfaces kind of goes through it too. So this should be enough to get it. And just ask me if it doesn't work. Explain the breaking thread methods. I did that. I mean, so basically you're going to take, here's the breaking thread here. So you're going to, I mean, it's not exactly clear from this paper, but this thing is pretty clear, you know. So you're going to make a fiber. So you have two components. You're going to make a fiber of one of the two components. And then you're going to make a sandwich of the other two and stick the fiber between the thing. And then you're going to stick it in a microscope, an optical microscope. So this is, they don't give it scale, but this is like millimeters here. This is pretty large. And it depends on the size of the fiber, right? So the R0 is the size of the fiber in this thing. So wherever Q is defined, R0 is the size of the fiber. So Q is smaller for bigger fibers. So smaller fiber gives you better resolution. So smaller fibers you can make and still see in a microscope, which would be about 100 micron, like a tenth of a millimeter. And so something like that would probably be the best system, because that's going to give you a bigger Q, and then Q's going to directly give you the surface tension. So it's basically the better quality data is going to come from small fibers. And then when you do that, then you just measure the starting diameter of the fiber, the R0, and then you're going to measure, or the A0, the diameter, and then you're going to just measure the peak, like the maximum here, divided by that. So the ratio of those two, alpha by alpha 0, is going to give you a log of alpha by alpha 0 is going to give you a linear function of time, which he shows in the, and that gives you this Q. Then Q is defined by this. So you know the original size. If you measure the viscosity, which it does in the paper with a viscometer, the plateau of viscosity is in the situation of very low shear. So you're in this region of low shear, like the Newtonian part of the viscosity. That's why you try to measure that. And then gamma is a number that they just give in the paper. There's a tabulated function. So somehow you just get that. I think it's in this paper somewhere. Gamma is right here. So you pick it out as a function of viscosity ratio. Well, that's why he has two viscosities, I guess. So this is gamma as a function of viscosity ratio. What viscosity ratio is. He has two viscosities. So it might be that's what the viscosity ratio is. Anyway, he just gets gamma. He doesn't exactly say. Anyway, he gets the two viscosity. He wants to use them to get gamma. And then R0 you measure, viscosity he measures, and then he measured Q with that, watching the oscillations grow, and then you get the surface tension, the binary surface tension between the two phases. It's kind of slick. That's a pretty good way to do it. I mean, all you need is a microscope, is in a hot stage. So a lot of people have those. In figure 7, Bergolo showed a situation with some Pickering motion. This is just like, what is a Pickering motion? What advantages it has. So I think mostly it's a serendipity kind of thing. Like people just found out that the stuff emulsifies something else by mixing random things together. So I'm not sure that I guess the advantage is it's cheap. So basically dispersing something with a surfactant, the surfactant's like engineered kind of and designed. So and it's kind of expensive, whereas like dirt or something, it's pretty cheap. Whatever powder you want to put in just happens to coat the phase, and then it creates an emulsion. So I think the advantage, not sure what the advantage is. It's just like it happens, you know, and you can use it. I don't know if it, let's see. I wonder what, like, where, let's see. If it says anything says where for food. cosmetics, pharmaceuticals, oil and gas. I guess it's used all over the place. So, but they don't give it, I'd like to see a specific example, like not generally food, like liquid marbles. That looks interesting. I don't really know of a particular example of a Pickering emulsion, but in research, people use it all the time, or they talk about it all the time. Colloidal silica. Yeah, so when would you use colloidal silica for an oil and water phase? Like you wouldn't, well, you could use that in cosmetics, I guess, you could use it in cosmetics. You could see that, but I'm not sure of an example where it's used. Anyway, there's a thing about, this is just like an interesting use of it, but it's not really a particularly, this isn't not an industrial material, it's something you run into. They show pictures of the Pickering emulsion, but so that one you're on your own. E. I mean, you can say what it is just from a wiki page or from whatever I said or from whatever he says in the paper. I mean, he gives the example of it in that the last he creates a Pickering emulsion by putting this surfactant in, putting this compatibilizer in. Like this is a mess, and that's a Pickering emulsion. So the polystyrene would stabilize the high density polyethylene phase for this case. So that's a good thing. And he can predict when that's going to happen if he has whatever one of these. He predicts, he discusses how to predict it from these mixing coefficients. It's not shown here. Basically, he says how you would get a Pickering emulsion. It's a quaternary system at that point. So it's got three polymer phases and this copolymer thing that he adds at 1%. So it's not so this has high density polystyrene and polypropylene in it, right? It's got three components, ternary, and then he adds this copolymer, makes it quaternary. But then he explains why that works, because so it's in the first picture in figure 1. So he says, like, you can predict just from the ternary spreading coefficients, the lambdas, that you would get like polystyrene near the high density phase and polystyrene near the polypropylene phase if you have this other component in it. So he predicts all the things that you observe. He predicts from the ternary numbers, but he doesn't actually predict the quaternary. He doesn't have a cartoon of how that happens. So it's a pretty good, well-written paper. If you read it, I think you can get a lot out of it in terms of how you would mix things and how this kind of thermodynamic analysis of it works for real systems. And it's it's important to recycling too. So it is a valid thing to look at. Anyway, that's about it for that stuff. I'm not sure what else we got. Any questions on the thing other than? So it's okay. Why don't we just quit early today? I think, I can do this stuff next week, this stuff on the Gibbs-Thompson equation. And it's a separate subject, so it's probably not worth jumping into now. So if there's no other questions, I'll just kind of end it there for today. That's all right.